Good morning, good afternoon, good evening, ladies and gentlemen. And in today's video, we're going to be taking a look at optimization. So there are multiple different parts of optimization. There's optimization for perimeter and area of rectangles, optimization of square-based prisms, and finally optimization of cylinders, okay? So first and foremost, what is optimization? Now, optimization is basically the process of finding values that would make a given quantity the greatest maximum possible amount given certain conditions. So for instance, you only have a certain amount of fencing to build a fence around your farm. What's the biggest fence that you can build? This would be an example of optimization. So let's see what we are taking a look at in terms of one of our examples here. So Ian has a summer job at a fencing company. A customer has purchased 32 sections of prefabricated fencing. This is like basically the wood that they cut down and they made it into the wood pieces. Each are 1 meter in length, and wants Ian to create a rectangular pig pen. So basically he's making a pig pen with this fencing with the largest area possible, meaning they want to fit as many pigs in there as possible. So this would definitely be an example of optimization because it's asking you to find the dimensions, the length and width, that would maximize how much pigs you can fit in here. Okay? Now, obviously, you have 32 sections of the prefabricated fencing, which means you have a max perimeter of 32 meters. So it's telling you here that you have 32 sections. This basically means that you have a perimeter of 32 meters. That's all you got to work with, 32 meters. So what we're about to do here is what we call optimizing the area. So what I want you guys to do is I want you to pause the video and I want you to try to figure out how you can make the maximum area here. Now you can try making a table here, looking at various widths, various lengths, but they still have to give you the same perimeter. So you can start with a table where you have width, length, and of course the perimeter. And I know that the perimeter, no matter what, has to be 32 meters. Okay? And finally, area. So you can try various lengths and widths. You could try, let's say, 2 for the width. Now, if it's 2 for the width, remember, no matter what at the end, you should get a perimeter of 32. So I know that 2 times 14 would be 28. And my width is 2, remember, because this is a rectangle, which means 2 plus 2. So if you have your triangle here, sorry, rectangle, you'd have 2, which means that would be 2. So now you want to get a length there that's going to give you this 32. So it could be anything as long as you add up to 32. So 2 plus 2 is 4. 32 minus 4 is 28. Which means each one should be 14. And 2 times 14 is 28. So your area here would be 28 meters squared. Okay, and you can keep trying different ones. Is that the biggest area I can get here? I don't know. Keep trying. So if you try 4, which means I'd have to use 12. Still has to be 32 meters. 4 times 12 is 48. Is that my biggest? I don't know. Keep going. So try 6. Try 10. Still has to be 32. That's 60. So you're seeing I keep going bigger and bigger and bigger. Let's keep trying. Let's try 8. Now if that's 8, that means the other one has to be 8. Still gives me 32. 8 times 8 is 64. Alright. Now you can keep going. You could try a 9, you can try 10. If I tried 9, then you'd have a 9 times 2, which is 18. If I took 18 away from 32, that would be 14, which means each one would have to be 7. And 9 times 7 is lower. Let's do this. So, basically what you're seeing here is, I'm noticing that my width of 8 and 8, where they are the same, is giving me my biggest area. That's interesting. So the maximum area here would be 64 meters squared. So what do we notice as our width and our lengths were getting closer and closer to being equal? The area was getting bigger and bigger. So this shows us one important fact, that is, a square where all sides are equal will always give you the max area. So how do we turn this into a law then? Okay, so let's go and check into the example here. So in part B, they're asking, suppose the customer decides to use 40 meters of fencing instead of 32 meters. So basically now they're telling you that this is your new perimeter. Okay, how would you make this fencing? So if I need to get 40 meters, we found out that the best way to optimize the area is to make a square, not a rectangle, which means I need to have all my dimensions to be the same. So if I have 4 sides in your square and I need to make 40 meters for my perimeter, then 40 divided by 4 would give me 10 meters, which means each side should be 10 meters. So the customer in this case should use 10 meters for his length by 10 meters for his width. And this would give me my maximum area. Now you can try this out and you can draw the rectangles and find their areas, and just to prove that you're correct. And you're going to see that whichever things you try, so let's say I tried 7, well, if I use 7 and I need to get to 40, so that means you're going to have 7, 7, so that's 14. That leaves you with, take 14 away from 40, that's 26. So this should be 13, and that should be 13. So if we try this, you'll get 7 times 13, which is 91. Okay. Now, originally, if I did 10 times 10, I'm going to get 100 meters squared. So, no matter what you choose, you're going to come to the realization that to find the maximum area, so let's make a rule here. Area, your sides are always going to be equal to the perimeter divided by your sides. Which is what we did here. We took our perimeter, divided by the total number of sides because we want to make a square, and that gave us 10 meters. Okay. Now that's what happens when you wanted to find a maximization of 4 sides. Let's just do one more example and then move on to another type of question. So now assume that your perimeter is 64 meters. If I want to maximize the area, let's use our formula. That means I'm going to take the 64. I'm making a fence, which means the 4-sided shape. So that's going to give me 4 goes into 6 one time, leaves you with 2. 4 goes into 24 6 times. That means that I should have 16 by 16. Okay, and that should give you your biggest area. So let's take a look at a new scenario. So let's take a look at this example, and you'll see that here Ian's customer decides to use an existing hedge. So he has an existing hedge here, let's say. And look at my amazing art skills. Yes, that's my hedge. For one of the boundaries of his pig pen enclosures. This means he will only use the prefabricated fencing on 3 sides. So let's say on this side, this side, this side, and of course, this side is taken by the pre-existing hedge. He still wants to get a maximum area in this pig pen. So if you draw another table, try different widths, different lengths, you're going to find after playing around a bit that the greatest area came from when you had 8 times 16, which would give you 128 meters squared. What's the relationship here? Well, 16 is half of your perimeter. And remember, the perimeter here is still 32 meters like in the first example. So if I did 32 divided by 2, I'm going to get 16. Okay? So that came from dividing our perimeter by 2. But then, how do I get the 8? So the 8, if I do 16 divided by 2, that gets you your 8. So overall, what is my rule here? Well, the rule is your length, or your width, could be either one, needs to be double the other one for you to have a maximum area when you're only dealing with 3 sides. So, therefore, when dealing with 3 sides, you take your perimeter and divide it by 2. This will give you your width or length, however you want to do it. And then you take your width that you just got, divided by 2, and that will get you your length. So let's try a different perimeter and see how this works. So once again, for part B here, assume the perimeter is now 40 meters. Okay? So using our formula, P is equal to 40. So I'm going to do 40 divided by 2, which is 20 meters. This is my width. And then I'm going to do 20 divided by 2. It's going to give me 10. That's my length. So to maximize the area, I need to do 10 by 20. And that's maximizing for the perimeter of squares and rectangles. The next thing we're going to look at is how to do the same thing for cubes. So let's move on to that. So we talked about 2D. Now we're going to move into the realm of the 3D. And in the 3D shapes, I want to start off with a general question here and say, how can you compare the surface areas of square-based prisms with the same volume? Okay, so let's assume volume is equal to 16. So let's make ourselves a little bit of a pyramid here. So length, width, volume, and surface area, just like we did before. Now, of course, the volume all the time has to be 16. 16. 16. So here you're going to have to try different things. Now remember, when you're looking at the volume of a square-based prism, the volume formula is always going to be length times width times height. Okay, actually forgot the height column here. Let's go height here. So what you have to do is you need to make sure that whatever you pick for your length, your width, your height has to multiply to give you 16 each time. And we're trying to maximize our surface area here. So you could try out different values. So let's say my length and width were both 1. Okay. Well, 1 times 1. That's not 16, which means my height would have to be 16. So 1 times 16 will give me 16. That works. And remember, for surface area, you're basically going to take 4 times your height and add to it 2 times your other sides. So 4 times 16 plus 2 times 1. It's going to give me 66. We're just using the square-based prism formula here. All right. Now what happens if I did 2 and 2? Well, if I did 2 and 2, 2 times 2 is 4. I still don't have my 16, so my height's going to need to be 4. That's going to get me 16, so that works. So now what you end up having is you're going to have 4 times 8 plus 2 times 4. It's going to give you 40. Okay, remember we're just straight up using the formula here. Now what happens if I decided to use 4 and 1? Okay. Well, if I used 4 and 1, then this would have to be 4. So when you do your calculation, you're going to get 48. All right. What happens if I used the same ones for all of them? So try 2.5, 2.5, 2.5. Because 2.5 times 2.5 times 2.5 is going to give me 16. When I do this calculation, I'm going to get 37.5. Okay? So when I do this, what happens when you have 3 of the same sides? Your length, your width, your height are all the same. That means you have a cube. A perfect cube, actually. And what happens when you get that is you minimized your area. So you got the minimum surface area by multiplying your length, your width, and your height. This is also what we would call the optimal surface area. Okay? So, what should we be doing here? We should always make sure that we have the same length, width, and height. So how would I do this? Let's look at an example. So in this example here, you can see that it says, the Pop-A-Lot Popcorn Company ships kernels of popcorn to movie theaters in large cardboard boxes with a volume of 500,000 centimeters cubed. Remember, the second you see cubed, that means you are talking about volume. That's your volume. My volume is 500,000 centimeters cubed. Okay? Determine the dimensions of the square-based prism box to the nearest tenth of a centimeter that will require the least amount of cardboard. So least amount of cardboard. That means you want to minimize your material. So we found out on the other page that the best way for that to happen is for the length to equal your width to equal your height. Okay? Now, if I know my volume is 500,000 and I want three things to be the same that are multiplying, well, if it was just two things, length times width, we would take the square root. If it's three things, you take the cube root. So assume that they all are equal to x because they're all the same value. That means I have x times x times x is equal to 500,000, which means x cubed is equal to 500,000. So I would need to take the cube root of both. So the cube root of 500,000 is going to give me 79.4 centimeters. About. You're going to have to round it. So therefore, your length should be 79.4 centimeters. Your width should be 79.4 centimeters. Your height should be 79.4 centimeters. And that is going to give you the dimensions that will minimize least amount of cardboard material. Okay? Now, if you want to find out the exact amount that you're going to use, so let's say in part B, they want to know the amount of cardboard. Whenever you see them asking for the amount of cardboard, that basically is them telling you with big bright letters that they are looking for surface area. And I know the surface area equation. It's going to be, in this case, 6 times length times width. It's going to be 6 times 79.4. 79.4, which is going to give me 37,826.2 centimeters squared. So, in general, my general equation then is always going to be to find my side, I need to do the cube root of the volume. Okay? Likewise, if you want to be able to find, let's say, the side and you were given, so this is if you're given volume. Let's say if you're given surface area. So I'm given my surface area. Then, instead, what you're going to have to do is take this formula. You're going to do, if you're looking for your side, so surface area is equal to 6. Let's use S for side. Then I'm going to have to get the S by itself. So divide both sides by 6. And to get rid of the squared, I'm going to have to take the square root of both sides. So that's going to leave me with my side is equal to the square root of surface area over 6. So if you're given your surface area, you're going to do the square root of your surface area divided by 6. And that should give you your sides. All right. And that's how you find the minimized area for the cube. All right. One last thing, we're going to be looking at cylinders. Okay, so finally, the last thing we're looking at is how you optimize for cylinders. So what I want you to do here, just as we did in the other ones, is I want you to investigate how the volume of the cylinder changes as its radius changes. Okay? So I want you to say, let's say the surface area is 375 each time. All right, so let's make our table. So radius height. What else do we need? We need volume. And finally, surface area. Now, obviously, my surface area is always going to be 375. All right. So let's say we could go many different radiuses. Let's say we go 1, 2, 3, 4, 5, 6, 7. Let's go up to 7. Now, if my radius is 1, and remember, you need to get a surface area of 375, and you can do your calculations for this, then my height should be 58.7. And my volume, which you remember is pi r squared h, would have to be 184.4. Okay, and then you can keep going here. You're going to keep getting your values. You're going to get 27.8. You're going to get 16.9, 10.9, 6.9, 3.9, and finally 1.5. All right, and that would give you the accommodating volumes of 349, 3, 477.8, 547.9, 541.9, 441.1, and 230.9. Okay, so all I'm doing here is I'm using the surface area equation to find my other things, because I know that no matter what, I should get 375. All right? So, what is the maximum here? Well, you can see the biggest is right around here. So the biggest it gets is right here. All right. So what does that mean? Well, what's my height in this regard? My height would be equal to the diameter. Now, so when you're looking at getting the maximum here, when is it happening? Well, here you're having your height, you're having your radius, and each time you're getting bigger and bigger and bigger and bigger. The second you get to the 4, it starts going smaller past this point. What's the relationship between these two? Well, my radius is 4 here, which is pretty close to getting 10.9 if I doubled it. If I doubled it, obviously I'd be getting 8. Okay? But it doesn't quite give me this. All right? So how can I predict it even better? So we can predict it even better by using the surface area equation. So let's do this. So surface area, you guys remember this, is equal to 2 pi r squared plus 2 pi r h. All right. Now, let's assume h is equal to your diameter, which is another way of me saying it's equal to 2r. So if that's true, let's put it in. You get 2 pi r squared plus 2 pi r times 2r. This is my way of getting rid of the h so that we're only working with one variable. Okay, so that way we're only having to solve for one thing. So in this case, you're going to have surface area is equal to, let's bring our like terms together. You're going to end up getting 2 pi r squared plus 2 times 2r, which is going to give you 4 pi r squared. These are both rocking the r squared, so I can continue to take them as like terms here. That's going to give me 6 pi r squared, because they both have pi r squared, so they're both like terms. All right. Now if I want to get r by itself, I'm going to divide both sides by 6 pi. And if I want to get rid of the squared, I'm going to do the square root of both sides. So that's going to leave me with surface area divided by 6 pi, and take the square root of that. So my radius should be surface area divided by 6 pi, take square root. That will give you your radius. And that is when my height is equal to 2 times radius. Now this should work every time. Let's try this out in an example. Okay, and finally here it's saying to determine the dimensions of the cylinder with maximum volume that can be made with 600 centimeters squared of aluminum. The second I see squared here, I know that this 600 is my surface area. Okay. Round the dimensions to the nearest hundredth of a centimeter, and then they're asking us after you do that to what is the volume of the cylinder to the nearest cubic centimeter. All right. So let's figure the first one out first. Now, if I am giving you the surface area, that means you can find your radius and you can find your height. But to find my height, I need my radius. Okay? So my radius, remember, is the square root of the surface area divided by 6 pi. So that should give me square root of 600 divided by 6 pi, which should give me about 5.64 centimeters. Okay. Now, if I know my radius is 5.64, that means I can find my height, which is going to be 2 times 5.64, which is going to give me 11.28 centimeters. Okay. So, therefore, my dimensions are my radius is 5.64 centimeters, and my height is 11.28 centimeters. Now, if I've got my radius and I've got my height, I can find my volume. And to find your volume, remember, it's pi r squared h. So you're going to have pi, and instead of your r, you're going to have 5.64 squared times 11.28. And that's going to give you 1,127 centimeters cubed. And that's it. So, there's only one more relation in terms of what you would see here, and that is the relationship between what happens if you're given your volume. So if you're given surface area, then I know I can find my radius by doing surface area divided by 6 pi. Well, if I am not given that, well, say I'm given volume. Let's do the same thing we did before. So you're going to have your volume equation, pi r squared h, and if you want to solve for r, you're going to move things around here. So I'm going to have the r squared here while I divided both sides by pi h, square root both sides. So r is equal to v over root h. Okay. Now, I can go even further here because I know that my h is 2r. So I can change this even more because let's say I don't even have my h. So what I can do is I can go even further and put in the 2r for the h. So if we do the same imperative rule here, you're going to get v is equal to pi, well, 2 pi r cubed. So you're going to have v divided by 2 pi is equal to r cubed. So therefore, let's finish this over here, r would equal the cube root of volume over 2 pi. That way, you're only really relying on your radius and not having to rely on having both your height and your radius. And of course, these formulas would work every time. I hope this has helped everyone in terms of optimization in all three of these different types of scenarios. Please let me know if you have any questions or concerns, and have yourselves a great day. Bye.